In this video, we'll take a look at graphs of exponential functions. So if we graph the following on the same set of axes, we have y is equal to 2 to the power of x, and then y is equal to 2 to the power of negative x, or remember that negative powers make fractions. That would be 1 over 2 to the x, or 1/2 to the x. What our graph looks like, and we looked at this graph in the previous notes, 2 to the x, when x is 0, y is 1, 2 to the power of 0 is 1, 1 we get 2, 2 we get 4. On the other side, when we put negatives in, 2 to the power of negative 1 is a half, negative 2 is a fourth. So what happens is our function increases without bound as x approaches infinity, but as x approaches negative infinity, the y values approach 0. So as x approaches, and if you remember, our y values approach 0. That's a horizontal asymptote. So before we take a look at 2 to the negative x, what are the characteristics of y equals b to the x? The domain of the function is all real numbers. We were able to put positive, negative, and 0. But the range of the function were greater than 0. So the y values are 0 to infinity. The y-intercept is the coordinate 0, 1. X-intercept, there were none. It does not cross the x-axis. If b is greater than 1, which is our situation with 2 to the x, if you read your graph from left to right, your function is always increasing. If it's always increasing from left to right, it's also called exponential growth. And then we'll take a look between 0, when b is between 0 and 1, 1/2. We'll take a look at that graph in a second. Our graph of our exponential function is 1 to 1, and it has an inverse, and the asymptote is the x-axis. It's the horizontal asymptote of y equals 0. So if we graph 2 to the power of negative x, remember when we make x is negative, it reflects over the y-axis. So you can think about this as a reflection over the y-axis. This coordinate stays the same. And there's our reflection over the y-axis. So what happens when we have 1/2 as our growth factor, our exponential function is decreasing instead of increasing. So if your growth is between 0 and 1, it's decreasing, or we call that exponential decay. So what we want to be able to do in this section is take a look at an exponential function, y is equal to b to the x, and graph using transformations. So our families of functions, in this case, y equals 3 to the power of x is going to be our function that we're going to transform. Could have just as easily used 2 to the x, but 3 to the x is the function if you plot a few points. When x is negative 1, the y-coordinate will be 1/3. When x is 0, the y-coordinate is 1. And when x is 1, the y-coordinate is 3. So 0, 1, 1, 1, 2, 3, negative 1, 1/3. So our exponential function 3 to the x increases a lot faster and decreases faster than 2 to the x, which makes sense because the growth factor is higher. And actually over here, I want to get a better. When we get to 2, 3 squared would be 9, so this is a lot steeper. All right, so remember our transformations from before. If we take 3 to the power of x minus 1 plus 2, what happens to the graph of 3 to the x? Well, if we take positive x minus 1, we're going to move our graph to the right 1. Plus 2 moves the entire graph up 2. So think of each of these coordinates moving, and also the horizontal asymptote moves. So if we're moving the entire function up 2, the horizontal asymptote also moves up 2. So I'll dot that in. And every coordinate moves to the right 1 and up 2. So I'll take each individual coordinate and move it to the right 1 and up 2. So this 0, 1 to the right one, up 2. This coordinate to the right one, up 2. And this coordinate to the right one, up 2. So our new function is a transformed version where the horizontal asymptote is now the equation y is equal to 2, and then 2 points on my graph are the point 1, 1, 2, 3, and the other point is at 1, 2, 1, 2, 3, 4, 5. All right, what else can we do to the function? We saw that if we take 3 to the negative x, that's actually the graph of 1 over 3 to the x, or 1/3 to the x. So this time our function is the graph of 3 to the x reflected over the y-axis. So I'm going to start with that function. There's 1/3, negative 1, 1, 2, 3. So there's our function 1/3 to the power of x. What transformation am I going to do? Now I have 3 to the power of negative x plus 1. Okay, you would think you would move to the left 1. But remember, we're adding to that 1 to the x, but that x is negative. So you have to write that as a negative factored out, x minus 1. So we did reflect it. We reflected the graph like we did here, but it's actually moved to the right one instead of to the left one. So it's this graph moved, each of our coordinates is moved to the right one space. Our horizontal asymptote didn't change because we didn't move up or down, but our coordinates changed because we moved to the right one. So what you'll have to do on homework is graph quite a few of these. So I've got an example on how to graph exponential functions. So to draw the graph of 1/3 to the power of positive x minus 2 plus 4, analyze the equation first. This is the graph of the equation 1/3 to the power of x, translated 2 units to the right and 4 units up. If you graph both of those on the same Desmos graph and create a table, this is what you end up with. Let me make that a little bit larger so you can see it. So there's 1/3 to the power of x is the graph in green, and then 1/3 to the power of x minus 2 plus 4 is the graph in red. When you graph these in Lumen, they're going to want you to identify the asymptote and 2 points on the graph. So if you take a look at the red graph, the horizontal asymptote is up at 4 because our graph moved up 4 units. And then 2 points on the graph, you can think of it as transforming this point 0, 1, and maybe transforming this, let's see, another point. Negative 1, 3. We've got them. I've made a table of values so that you could see. You have to identify 2 points on the red graph within the window. So 1, 7 and 2, 5 are 2 coordinates that you could use. So there's 2, 5, and here's 1, 7. So when you graph these on our Lumen, you have to identify your horizontal asymptote first, and then select 2 points on the graph. And that's how the graphing tool works in Lumen OHM. So try the next one. Draw your graph of 1/2 to the power of x plus 3 plus 3. First of all, we describe how the function 1/2 x to the power of x is being transformed. We're moving that graph to the left 3 and then up 3. Then graph using Desmos so you can see where your coordinates are. So I'm going to type in 1/2 to the power of x. I'll use g of x. And then I'm going to add the function f of x equals parentheses 1/2 to the power of x plus 2. I'm going to put that in parentheses too, x plus 2. And then my other value was here it is. My other value was plus 3. Sorry that took so long. Okay, so plus 3. So if you can tell by looking at the graph where your points are, that's 3.25. That's not an integer point. Negative 24 is an integer point. And then see if you can find another integer point on the blue graph. And it looks like we've got one here. Hard to tell. So if you can't tell, make a table of values. So we're going to add a table and put some values in: -2, -1, 0, 1, 2, 3. And then let's put in our f of x1 and see if you can find integer points. So at -2, there's a 4, -1, 0, 1, 2. Let's see here. So after you take a look, let's put in a few more points and see if we can find an integer point. -4, so I need to go maybe -4. I'll put it down here. So I'm not going to get any integer points. -4, there we go. -4, 7. There's my other integer point. So what I would use, identify the horizontal asymptote. Since we move the graph up 3, the horizontal asymptote is at y = 3. And then my two integer points were at -2, 4 and -4, 7.